Hello everyone and welcome to our YouTube channel. We are working on a series of videos on openmp and this is our 12th video on that series. If you haven't checked out the previous ones, do watch them to get a better idea of openmp and a better understanding of this and past videos. So today we'll be studying pi calculation. So almost all of you might have heard of the number pi. So it is something like 3.14 and it goes on because it's an irrational number, so it does not have an end. It will continue on even after all the decimal places. So how do we actually calculate the value of pi? The value of pi is given by the integral 0 to 1 4 by 1 plus x square dx. So if we calculate the value of this integral, we will get the value of pi. But we cannot just give the complete integral as it is to the computer. We'll need to break it into a program for the computer to be able to understand. So imagine this. Let's say I have a graph. Please excuse my drawing. It's not very good. So it's supposed to be a linear graph. It somehow made it like that, but no problem. Let's get to the explanation. So, and pi is the curve on this graph. Okay. This curve is the value of pi. This curve is pi. So how do I calculate this? So since we're talking about the integral, what is actually an integral? Integral is the value under this curve, and that is equal to value of pi. So one way to find out the value of this curve is by dividing it into small rectangles, extremely small ones, so that it becomes a kind of a rectangle. And we all know the area of a rectangle is very simple, length into breadth. And then I'll simply add the area of all the rectangles within this curve and I'll get the value of pi. So this is the computer way to achieve this. Okay, so now let's see how we are doing it. So this is the classical method to do it. What I mean by classical is without any parallelization, and so it will be running using a single thread. So I have a long, so static long. Static means I do not want this variable to change, and long because I want the value here can be bigger than the 32-bit allows me to. So that's why I need to use long instead of int. Then we have double step. I'm defining variables. And then we go to int. Inside the main function, we have I. We're defining I. Now I've defined the value of a variable sum is equal to 0.0. And now I'm finding the step. So what exactly is the step? What am I trying to achieve here? I am breaking the curve into small steps. And what's the size of the step? 1 upon number of steps. So number of steps is how many rectangles I want, and what will be the size of each step? That will be 1 upon number of steps. And next we have the for loop. Very simple, not very complicated. It's a simple for loop, and this is a very this is where the actual mathematical part starts. So we have x is equal to 1 plus 0.5. So why 0.5? Why not something else? So 0.5 is the midpoint of it. So if you see in the okay, not exactly that. So in the rectangle, a computer doesn't know where to calculate the area from. So it can do from the right side, calculate from the right side, or the left edge. It does not know where to do it. 0.5 tells me the midpoint. 0.5 is the midpoint, and it tells the computer calculate the area at this point. I don't care if the area is different because it's a curve at the end of the day. So the area at this point and area at this point will be a little bit different. So I will take the midpoint of these 2 points and find the area there. So this is what 0.5 achieves, and I'm multiplying it by step. So step, since it's the width of each rectangle, I multiply it, I get the area of the rectangle, and then we have sum is equal to plus. So we are adding to the variable sum, and I am dividing it by 4 upon 1 plus x square, which is the formula for pi. Dividing it, adding it to variable sum, so that way I can calculate the area of the entire curve, and I'll get pi is equal to step times sum. So whatever is the value of step, I'll just multiply it to sum, and I'll get the value of pi. So that's printf, and that's the value of pi will be printed here. So let's go to the parallel method. And in this, you might have noticed, we are running this program. We have to run this program for a very large number of steps. And what's the most intensive part of this program? This for loop. Because it has to run for a long time. And since it's a singular loop, since it's singular, that means it's classical, no parallelization. Only single thread will need to multiple times pass through this thread, pass through the loop, and calculate for each. So it will take a lot of time for a single thread to do it. So let's parallelize this part. And it's very simple. I'm just defining the variables, nothing new here. And then there's pragma parallel. So this is the first difference. On parallel, it creates a set number of threads. Since I haven't set any number, by default it will go to 48, because that's what the hardware allows. So, and double local, for this program I am creating a local variable, and I have pragma omp for. So omp for, so why do we use for? Because I want to use a for loop inside of the parallel. If I use for loop without this pragma omp for, then what will happen is each thread, so all of the 48 threads will run this for loop this number of times. That is not desired. I do not want to triple my workload, 48 times my workload. What I want to do is reduce it. So I will break this workload into small sections and distribute it to the threads to perform, to work on. And with the for, I haven't used any clause, and that means it will, openmp will use the default one, and by default the scheduling is set to static. Chunk size will be calculated depending on how much work needs to be done. It will automatically set the chunk size. Then I have pragma critical. Why do we need? Oh, sorry, I skipped the for loop. It's the same as the previous one. The for loop is exactly the same, not much difference. Local 0.12, instead of sum, now I'm just doing local. And why is that? Because I need to avoid race conditions. So I am updating the local variable here so that I can avoid the race condition. And then inside a critical block, so that means only one thread will update this block at a time. And I am doing it the sum plus local. So I'm adding the local variable to the global variable sum. And then I'm just simply multiplying it by step value to get pi. Now I have pi is equal to this. It will return me the value of pi. Let's look at a live demo of it. So I'm currently logged into a HPC Param Rudra, and I am inside the login node right now in the openmp programs directory. I have loaded the Intel 1 API compilers for openmp compatibility. And these are the programs that we will be compiling: pi calculation and openmp pi calculation. So let's get to compiling them. Let's first do pi calculation, just to get of idea. Calculation.c. No connectors required in this one. Do a dot out. Yeah, so I get value of pi is 3.14. So since I'm in the Linux system, I have the option to time this executable as well, and it can be done simply by typing time.a.out. It will give me how much time it took to perform this operation, and it took like 0.656 seconds. So it's very less time taking. It's already very efficient because the system that I'm working on is very powerful. So let's compile the openmp program. One thing that you need to note is that since the system I am working on is extremely powerful, it's one of the most powerful HPCs currently in India. So that is why the output times is so low, even for a single threaded program. But if you are running this program on your own computer, which is not as powerful, obviously the output times will vary by a lot. So let's compile this program, and then I can simply, let's first run it to see, yeah, it is working fine. 3159. So they're quite accurate. They're a little off at the end. Well, that is because if I want better results, I'll have to increase this number even more. It's already quite big. So let's time it. And now I have got a reduction of more than 10 times. So now the time is 0.026. That's a reduction of about more than 10 times, actually, close to 30. So this is the type of power that we have when we are working with the parallel program. So the original time is also quite low, but that is in respect of this computer. But if you are using parallelization, if you are parallelizing the programs, then you can achieve these type of results even with your computers, even with your devices, which are much less powerful. So this is a very practical application of openmp, and very useful one as well, because pi, calculating the value of pi is it may seem very useless to you guys, because 3.14, that's just the value of pi. Why do we need to go further? Because in real world systems, we need to get as accurate, where we need to make predictions. The more accurate the value we are using, the more accurate will be the result. That is why we need to increase that increase the number of steps even more to get a more accurate value on the accurate value for pi. So that is it for this video. Thank you for watching.